So hello and welcome back. We've done quite a good job in which we've seen how the various systems they couple with each other and how do they couple out with each other, how do they hybridize with each other in all interesting architectures when we use the concepts, when we use the paradigm of the ensembles or the modular neural networks as we've been seeing in the last couple of hours. So today the agenda is a very small agenda where we'll carry forward only one small task wherein we'll try to see out how is it that I can have some kind of evolutionary principles added out into this evolution of the modular neural network and how can I use it for problem solving. Because as we migrated from the neural networks to the evolutionary neural network, there were some things that were noted down, there were some limitations that were noted down, and we said that we need to use the optimization power, the evolutionary power of the evolutionary algorithms in order to completely remove those limitations. If not completely remove, then remove it to a good extent. And as a result, we were getting in better varieties of neural networks, which were known as the evolutionary neural networks. Now, since a hybridized neural network with itself, a modular neural network, is nothing but a more complex form of neural network, it is bound to have the same limitations. It is bound to have in the same limitations that a single neural network has. And since it is bound to have the same limitations, we ought to remove out these limitations. And how do we remove these limitations? By the added advantages of the evolutionary computing. So here we would be adding in the paradigm of evolutionary computing, and we would be trying to make in modular neural networks. Now, the general discussion that follows, again, there are numerous models that are possible. There are numerous varieties of models that have been constructed out to make evolutionary neural ensembles, that evolutionary modular neural networks. Some of these models, some of them they use genetic programming, and by programming techniques they try to evolve in the right architecture of how the modules interact with each other, what are the duties, responsibilities of the various modules, what are the connections. Sometimes they try to evolve out the specific neural network architectures and which are then combined in some specific format. Some of these models, they try to solve out this problem using other invariants of the evolutionary computing, and of course many invariants of the neural network model that is being followed out as well. Now, one of the very simple things that would come out in mind is that evolutionary computing is quite a simple technique. All I need to do is that I need to make sure that all the parameters are embedded right inside my genetic individual. So wouldn't it be very simple to do? Wouldn't it be a very simple kind of exercise in which all that I do is that I take in my individuals, all that I do is that I take in my individual and I embed all information relevant to the system right inside these inside the genetic individual, and then the genetic algorithm would carry out the rest of the task. But the important point to realize this is that what we saw is that the evolution of a single neural network, the evolution of a single neural network is a highly dimensional problem. It is highly dimensional because of a very complex and a highly dimensional search space. Even for problems with lesser number of inputs might be a single output and smaller number of neurons in the hidden layer. Even that simple kind of a problem, it was highly dimensional in nature, and hence it wasn't really possible. For us to carry out evolution, and we carry out this evolution using some local search strategy. We carried out this evolution using some kind of local search strategy. What the local search strategy did, it enhanced the individual, it made it appear right inside to appear right inside some local minima, and then the genetic algorithm could coordinate the various individuals in search for the global minima and in trying to escape out from the local minima. That is what it basically tried to do out while we were performing. And of course we saw that since the problem was highly dimensional, it was a lot time computation, so if we could only execute a smaller number of individuals and a smaller number of generations, unlike the other evolutionary computing approaches, and as a result of it, we had to of course wait a lot to get the final optimal neural networks. Now when it comes to the problem of modular neural network, where there is some problem being solved by a set of modules, let me say that there is an integration phenomena over here, and that does the integration of it. Each one of these are neural networks and so on. Even if I take the architecture of these neural network fits and I try to generate an individual such that these are the parameters of NN1, these are the parameters of NN2, and these are the parameters of NNK, the size would be massive. The effective size will be massive, so that is not something that I can carry forward. So that is not something that I can carry out here because of this highly dimensional size. So if this is not I can carry out, how is it that I carry out this task? I carry out this task using coevolution or the cooperative evolution. I'll be using in principles of cooperative coevolution to solve this kind of problem. Now the principles of coevolution we've already studied. Just to repeat, is that what we do is that we break the main problem into a variety of sub-problems. So there was a main problem that was too big, it could not be evolved. So I break it out into a variety of sub-problems. Each one of these are nothing but modules that help me in solving the main problem. These are all related problems, problems of the same kinds of a smaller magnitude. These are all problems of the same kind of a smaller magnitude that I simultaneously evolve. These are all the problems that I simultaneously evolve which are of the same kind. And then what do? I apply some mechanism of selection of modules. So this evolution, it goes on. These all represent the individuals, and the evolution of this goes on and on and on, and there is some mechanism by which I select these modules, normally a genetic algorithm by which I select the modules. Using this genetic algorithm, all that I do is that I select the best modules that together give a very high performance to this problem. Now when I integrate all these selected modules, selected from here, I get in a solution to this main problem that I was looking for. I get in a solution to this main problem that I was looking for, and as a result, this main problem is solved. What is important is that all these individuals must evolve in a cooperative manner, where this individual helps this individual to attain in better characteristics, and this individual helps this individual to attain in higher characteristics. So there is some cooperation in evolution that is essentially required. There is some kind of cooperation that is essentially required. And how do I carry forward this cooperation in order to carry out this task? How do I carry forward this cooperation this cooperation mechanism over here? It is by using the evolutionary pressures for the same. So I need to use the evolutionary pressure for the same, and I will be modifying the fitness function in order to carry this out. I'll be modifying the fitness function in order to carry out this task. And as a result, what I'll do is that the individual which may not have a very high fitness, the individuals which may not at all have a very high fitness, I'll still give them a high fitness value only because they help the other individuals in attaining the high fitness. So even if you yourself do not have a high fitness, because of you, if the other individual has got a high fitness, that individual is given a high fitness count. So that is what the basic principle of cooperative coevolution, a part of it of course we discussed earlier, is in making the individuals cooperate with each other for the evolutionary task. Now, how do we use it for this problem where I have to evolve a modular neural network of this architecture? So what do? I have in a big problem that states I have to evolve a modular neural network. I have a big problem that states I have to evolve out a modular neural network. Of course, I may not be able to solve out this problem. I may not be able to solve this problem out because of high dimensionality that we have just seen. So I need to do something. And what do I do in order to make this problem solvable? I decompose it out into smaller problems. And my smaller problem says that evolve best modules. So my smaller problem is that I have to evolve in some modules. I carry out this task of evolution of modules, and after that the work that is left is select best combination of modules. So there are two tasks that carry forward. One is that I evolve in the best modules. So each and every neural network has got an independent evolution. All the neural networks, they evolve independently in a cooperative manner. Of course, it's not independent, it's cooperative evolution. All the neural networks, they evolve cooperatively. And then the task left is that how do you select out the best combination of these modules that have evolved. Now an interesting question would be that why don't we carry out independent evolution of the neural network, in the sense that each one of them is an independent evolution neural network, and that's again the reason states that if we evolve them independently without any cooperation, if each one of them will be an evolution neural network, they all will develop similar characteristics. They all will develop similar characteristics. If they all develop similar characteristics, they will be of no use to each other, because again the laws that we wrote down, the principles that we stated, that the individual expert performance needs to be as high as possible, and the performance or the individual experts needs to be as diverse as possible. They need to disagree as diverse as possible. The second principle will not hold good if we make that a normal evolution neural network for each one of these neural networks. And hence this cooperation phenomena is needed. So evolution here is carried out at two levels. The first level is known as the nodule level. This is known as the nodule level, and the second level is known as the network level. The first level is how do we evolve out a nodule. Of course, in neuro-evolution, when we talk about the neuro-evolution, we talk about the concept of nodule and network. So this is a nodule level, and the complete architecture that we get, that is known as the network level. So there are two levels of evolution. Both these evolution, they happen parallel to each other. Both these evolutions, they happen parallel to each other. And of course they are interlinked to each other, there is a dependency between them. Both these evolution, they go on parallel to each other. The first level deals with how do I generate in the best nodules. How do I generate out the best nodules that have got distinctive characteristics that can combine with other nodules to produce very good modular neural networks. How is it that I can generate the nodules that are very high performing, such that whenever they combine with other nodules, they produce a network that will be a very high performance. So that is what the first evolution tries to do in generating better and better nodules that have intrinsic characteristics in them for very good problem solving. The other level is the network level. What it does is that it tries to generate in the best combination of module to make the best modular neural networks. It tries to generate out the best of combination of nodules to make it the best modular neural network. Here the module that is used is ensemble in nature. It's an ideally and sometimes it becomes an interrelated word because the problem lies in how you model it up. Here in the discussions that followed, I will be normally using modular neural network to be analogous with ensembles, though they are not actually ensembles. So the first mod is at the module level, which deals with generation of better and better nodules, and the other deals with generation of best combination of nodules that makes up the entire network. Now again, an important question would be that in an evolutionary approach, all the individuals, they converge out at some point. All the individuals, they more or less converge out at some point. If the same thing happens out over here, if all the individuals, they converge out at the same point, how is it that my modular neural network or my ensemble will be optimal in nature? It will be good performing because the diversity would be all lost. As in every evolutionary approaches, there is convergence. All the modules, they converge out there at some point of time. The individuals, they have very less difference. If the same thing happens here, no matter what module you select, they are all similar, they are all alike. So how is it that my ensemble is going to be good? How is it that's going to be better? How is it that's going to perform good? Then again, the thing is that we modify the evolutionary pressures only for this reason. We modify out the evolutionary pressures only for this reason, and we encourage development of distinctive characteristics. So the various modules, they never converge. The moment they try to converge, they lose out their fitness value, and any nodule that tries to develop new characteristics, it's given a very high fitness value, so they all expand again. And hence diversity is maintained. Diversity between the various nodules is maintained, which is a very important property only because of the basic principles of ensembles, that diverse classifiers are needed. So we move on. The problem now that is there is that we have to make two genetic algorithms or two evolutionary computing techniques. One at this level, nodule level, the other at the network level. Both these techniques would run parallel to each other. So one iteration here, one iteration here, one iteration here, one iteration here, or one generation here, one generation here, another generation here, another generation here. They both run in parallel. So we'll see as how is it that we can do this up. Now since they run in parallel, I'll be having mostly parallel discussion over both of them. I'll have kind of parallel discussion over both these algorithms that are up. The first part is the individual representation. The first part is the individual representation. This will be done at a nodule level and it will be done at the network level. At the nodule level, what we have is all the weights and biases and the connections, they are all embedded inside. So this will be some collection of weights, biases, sometimes connections, and whatever we dealt with the evolutionary network. So all this information would be right inside the module level. All this information would be right inside the nodule level. This is what is the individual representation. Now a population of nodule, I take in a population of nodule. And again, once the individual representation has been done, it's ideally needless to say how the initial population will be generated. In the entire discussion I had, in all the other approaches I had said that it's conventional, so we don't discuss. Here I would just say that it's conventional, but we draw in, let's say, individuals out over here, I1, I2, I3, I4, I5, I6, I10, In, and so on. We make all these individuals over here. Each one of them is again the same vector. So again, that's conventional nature. We additionally drawn in a population of nodules. This is at any time t. This would be there at any time t. We made it a population of nodules out over here. At any time t, what I'll do is that, now this was the individual representation, this was the initial population generation. What I'll additionally do out is, I'll make in a set of evolutionary operators to modify this population to another set of population. I'll use in a set of operators to modify this population at any time interval generation t to give a higher generation t plus 1. That is what we'll be discussing out in some time from now. This problem requires no stopping criterion because if both the algorithms run in parallel, the stopping criterion is common to both of them. The stopping criterion is common for the nodule level as well as for the network level. The stopping criterion would remain common to both of them, and hence that can be collectively put up based on the fitness value or whatever. So this is what the population representation is all about. We migrate to the network level now. So this was the module level, this is network level. Network level, the problem is very simple. It just says select the best of the individuals. It just says you select the best individuals or the best modules that collectively make in the classifier. So let me say if I had k nodules per classifier, if I had k nodules per modular neural network, and my modular neural network of this form, that there was nn1, this was nn2, and this was nnk, some set of inputs. So all I have to do is I need to take in a genetic individual of size k. Each one of them is a pointer that points to some individual out here. Now remember, it's not a genotype representation, it's not a normal bit string or double vector representation. Here in place of numbers we've taken exactly pointers. Here we've taken exactly pointers. All my work would be on pointers. All my work would be on pointers. If they are pointers, then they would always point out towards something. They will always point out towards some kind of network. So that is a very simple network level implementation, and similarly there will be multiple individuals. That is what will make it the population pool up over here. I know this population at any instance of, I know this population initially, it's all randomly generated. I know this population, so I can generate a random population of the network level as well once the population of the nodule level is known. Once I know what is the population of the nodule level, I can get the population of the network level as well, where there will be multiple individuals like this, each pointing out towards some of the other individuals, and so on. So this is the representation of population at the nodule level, this is the representation at the network level, both going hand in hand. The next task to be done out is the application of evolutionary operators. The next task that is done is application of evolutionary operators. So again, I will use some very simple operators. Of course, the most complicated ones can be used, but I will use some very simple kind of evolutionary operators. Selection would be normal, it does not depend upon the individual representation. Of course, this is a linear representation, so most of the conventional things should follow. What I do out here in this population is that I apply the operator selection which is again there. I apply some replication and I apply mutation. It's an evolutionary network, so mutation would be a parametric mutation or a architecture mutation. It's completely evolutionary network. So you have both these mutations coming into picture. No matter how you represented it. Of course, I am not specified some specific criteria in which you can represent this. So there will be architecture mutation and there will be parametric mutation out here. And all these operators. When we are dealing at the module level, the first thing that we do out here is that there is a population of individuals that I have I1, I2, I3 here. Replication is like an elite operator. It simply says that the best P percentage of individual transfer directly to the next generation. It's just like using elite operator. The best P percent individuals will go directly to the next generation. That is what the replication would do. It will send the best P percentage of individual directly to the next population. What mutation would do is that it will select 1 minus P percentage of individuals by the selection operator. It will select 1 minus P percentage of individual, and using its own techniques it will carry forward a parametric mutation or an architectural mutation. Using its own technique it will carry forward either of these mutations. Now that is again specific to how you have represented the individual out over here, and how is it that you are carrying forward the evolution, how is it that you are carrying forward the operation of the operators. Most of it we dealt with the evolutionary neural network, where we saw in a couple of architectures, a couple of mechanisms that could do that. So this is what would be again very simple, the evolutionary operators. We applied in very simple evolution operator. We not carry forward crossover in this operation at all. If someone will carry forward any kind of operations or any crossover thing kind of here, so these are very simple evolutionary operators applied over here. At the network level also some genetic operators are needed, of course. That is the next point of discussion. So again I say selection, crossover, mutation, and all these can be applied. Might be an elite. Elite will send the best individual from one population to the other population. Crossover, I say, is simply a change of links. So if two individuals with some pointers here and there, if this crossover with some other individual with some other pointers here and there, I form in an individual. It can be 1-point crossover, 2-point crossover, or any scattered crossover. So I form in two children with all these links being exchanged. So again, exchanging binary numbers, exchanging real numbers, or exchanging pointers, it does not make any much of a difference. And mutation again can be that I change this link from this individual to a new individual. I simply change the links from this individual to a new individual. What sometimes can be thought that any new individual that is generated in this population pool, that might be given some kind of preference in how we select this in how we move this pointer. So mutation is just like I am moving in some pointer from here to there. What was pointing out towards something, I make it out point towards some other thing. That is how the mutation operator works. So again, very simple operators did not make much of a difference in the evolutionary operators. When I change the real numbers to actually pointers, a pointer-based individual representation. But the most important terminology, the most important thing that needs to be discussed is the last part that is left to be discussed, that is the fitness function. Because again I said that I will be so many times that I will be modifying the evolutionary pressures, I will be modifying the evolutionary pressures by the fitness function. How do I actually do that is the point that is to be dealt with the fitness function. So now the fitness function is again different for the nodule and different for the network. It's a different fitness function is there at the nodule level and a different fitness function is there at the network level. So we deal with them one by one. At the nodule level, what happens is that I need to first, because I have to carry forward a cooperative coevolution, I need to first pen down what is it that the evolutionary algorithm should look after. I should pen down what is it that I am trying to achieve. Now, one thing that I am trying to achieve is a high performance of eminence in which this nodule participates. What this criteria says is that if I add this nodule to any combination of nodules in an MNN, the complete architecture should have a very, very high performance. If I happen to add this kind of nodule to anything, it should have in very high performance. How this is possible? This is only possible if the nodule has in good problem solving characteristics. So it knows what the problem requires and it has those characteristics that are required to solve that problem. In natural world, we'll say that there's a problem, there's a task that needs to be done. The whole class of people are there who have nominated to this task. You need to make it a team that solves the task. Now each and every individual who has problem solving capability, who can himself solve the problem very well, needs to be promoted because he'll combine with other people and be very important for problem solving. So all these individuals who nominate, they need to have in high problem solving capabilities themselves. They need to have the characteristics, as many as characteristics as possible that are needed to solve the problem. And that is what we try to encourage out over here. So how do we do that? We inspect all the eminence in which this module is a part of. We inspect all the eminence which are formed using this module. Now one relationship should be clear, that every nodule is linked to multiple modular neural networks or multiple networks. So this module is linked to this network as well, this network as well, this module is linked to this network as well, and maybe this network as well. So every module is linked to multiple networks. There are multiple networks pointing out towards same nodule, and since they are multiple networks that are kind of pointing out towards the same nodule, so what do I say is that I select out, all that I do is that I select out best K networks which have this module. So if I'm trying to find out fitness of the nodule I, which have the nodule I try to find out the best K networks in this entire pool of network that have this nodule available in them. So that is the first thing that I will try to do. Why will I try to do this? So that the individual performance is high. This is known as the best K criterion. The second thing that I do is known as substitution. I'll sort all these networks in descending order of fitness value. I'll sort these networks in descending order of performance, with the highest performance being as top and lowest performance being right at bottom. I'll select the best K, or I'll select the k highly performing nodules or there are k highly performing networks. I'll find out what are the k networks that are very high in their performance. Now once I do that, I'll have in k nodules of very high performance. I simply do one thing. I delete a nodule from here and I replace it by this nodule I. I replace it by this nodule I, and then I see what is it that the performance is. I look at it, what is it that the performance of this network is. And why do I do this? I have selected in the best k nodules, the best k networks, so their performance was already high. I selected best k networks, so their performance was already high. Now I try to find out if the performance was high, that means all the various nodules inside that network, they were all having in all the characteristics, they were collectively having all the characteristics needed to solve the problem. They could collectively have enough of high performance in themselves and enough of diversity so that the ideal boundaries could be made. That's why the performance was very high. I look at it, if I replace one of these nodules with itself belonging to the same subpopulation, I delete the nodule having the same subpopulation as the nodule I, and I insert nodule I on its place, and I see what the fitness is. So this is what the performance that I get is what I call as the substitution. I call this as the substitution. What substitution tries to encourage is, it tries to encourage developing in good characteristics that are probably complement the other characteristics that are not there with other parts of the individual. It tries to generate in some unique characteristics. Now again, in the same analogy, what we want is that if it's a class and a committee needs to be formed to solve some kind of problem, we need some unique characteristics that are not commonly found. So we need to encourage these unique characteristics, be it found in any individual. So we need to generate give a high fitness value to these individuals who may not have good characteristics that are needed to solve the problem, but they have unique characteristics that help in problem solving. And because they are unique, then the other individuals do not have, and hence you need to give a high fitness count. And hence you need to give a very high value of the fitness count that you have. Now giving in a very high value of fitness count would even encourage the other individuals to develop these unique characteristics, and that is what is intended. We'll have more choice towards the later stages where the individuals develop unique characteristics. That is what substitution does. The third thing that I am trying to do is what is known as difference. The third thing that I'll do note in this is difference. What I'll do is that I'll again select the best k networks in which this nodule I is to be found. I'll select the best k networks in which this nodule is to be found. I'll delete this nodule from this module, from this network altogether. And then I'll note what is the difference in fitness value. So I'll select best k networks in which I is to be found. I found out its collective fitness I find out the fitness of all these k modules. I find out fitness of all these modules, and I see what is the difference when I delete these modules. So it is ni minus I. I see what is their difference in performance, that is the resultant of this module. If the difference is very high, if the performance dropped very high, That means this nodule was a source of some characteristics without which the performance suddenly fell apart. This nodule was possibly a source of some characteristics without which the nodule performance suddenly fell way below, and hence this was contributing some complementary characteristics to the network. Had it not been giving some complementary characteristics to the network performance wouldn't have reduced to that high amount. And if it's given some complementary characteristics, that means it has again developed in itself some characteristics that are needed for problem solving. It has developed in some kind of characteristics very essential for problem solving, and hence these are good. Development of complementary characteristics that aid in problem solving is very good. That's again into the same example. If I have a class, a person knows what is not present in the committee and he goes up and develops those characteristics, so unique characteristics being added to the system. So that is what exactly is my fitness function at the nodule level. My fitness function at the nodule level is nothing but best A1 times best plus A2 times substitution plus A3 times difference, and of course I will have to penalize in the number of neurons and the number of connections. I'll have to penalize the number of neurons and the number of connections. That is one. The second thing is that I may always use in some local search strategy in the individual nodule approach. I can always use in some kind of local search strategy that aids in the evolutionary process. So that is what is my fitness of any nodule I. Again, much of the what was stated initially has been met. I stated that we'll modify the evolutionary pressures such that development of good complementary characteristics are enhanced. That is what we did. I said that if the problems they converge, if all the nodules they happen to converge, any nodule that develops in good new characteristics, we'll reward it with a high fitness, so that they never converge, they always generate a unique characteristics. All that has been implemented by this modification of evolutionary pressures. Conventionally, in a non-cooperative evolution, only this could have probably been the fitness measure, but this is what carries out cooperation. These are the evolutionary pressures that reward cooperation, and that is why an individual having very poor fitness, having very poor best value, is given high performance if it leads to better fitness value of the other nodule which is a part of the same network in which this is participating. So cooperation is rewarded. That is what we did here, we rewarded cooperation over here. So the last part to be left out in this entire discussion of the coevolutionary neural network or the coevolutionary ensembles is the fitness value of the network, a fitness value of the at the network level. Now I have in a set of pointers, that means I have in k number of nodules that have already been selected. I have k nodules that have already been selected. These may be in the genotype representation like this, because again now in order to calculate the fitness value of the network, what I am doing is that I am carrying out a genotype to phenotype conversion of the nodule. So there is again a relationship between nodule and network. In order to calculate fitness of the network, I have to convert a genotype of the nodule into a genotype of into a phenotype. So I'll get in some neural network over here. I'll apply all those fundamentals of the ensembles. I'll pass on the inputs. I'll note down what the error. I'll calculate the output and note down the error. I'll calculate the performance. Now this is directly proportional to the performance of the resulting element or the ensemble, whatever the notation may be. This is exactly the performance of the eminent that I am looking for. So I can assign in the fitness function here. There's no K here. I can simply assign the fitness over here. So my task of fitness evaluation is trivial in this case. I already have the neural network in hand. It's just to be converted from a genotype to a phenotype representation out here. So in this way, what happens is that I simply take in as the initial module population network population. Now while stopping criterion is not met, I apply selection, I apply replication at PT, I apply mutation at PT, I apply some kind of let's say crossover at QT, I apply some kind of mutation, I apply some kind of elite operation all at QT, I evaluate fitness of, now let me say that this gives me PT plus 1, this gives me QT plus 1, this gives me PT plus 1, I calculate the fitness evaluation of PT plus 1 and I evaluate fitness of resulting PT plus 1. That's how I work about. So it's a very simple algorithm that will go on in parallel. It will keep on happening. So what I am doing is that essentially there are two parallel algorithms that are running, there are two parallel evolutionary computing techniques that are running in hand with each other. One is the evolution of the best nodules that have diverse characteristics, that have distinct characteristics, that have themselves have high performance. So all the principles of ensembles, they are kept intact because of the evolutionary pressures. And secondly, I have the module, I have the network level which generates the best ensemble. The best ensembles are generated. That's a simple genetic algorithm that's applied. Apart from the fact that pointers are used in place of real numbers or binary numbers, and they go hand in hand in this manner, and individuals they keep on generated. Most of the principles, in fact, if not all, I may have deviated a bit over some points or no point. This is what is known as CoeVNet, the cooperative evolution of neural network. This is what is just a very fundamentally used, a very widely used model that is known as the CoeVNet, the cooperative coevolution of the network. Of course, we haven't done the analysis over how does the fitness change along with time at the network level, at the nodule level. All those things can be visualized, but the important point to realize is that I have been able to solve in a very high dimensional problem. The problem was evolution of a complete modular neural network architecture which was very highly dimensional. I have been able to solve it a very highly dimensional problem using the principles, using the concepts of cooperative coevolution, where cooperation among the individual was encouraged, it was highly encouraged, and that is what we saw at the nodule level, how cooperation happens and how does it ultimately lead to a good ensemble. And how does it lead to a very good ensemble that can be very nicely used for problem solving of everyday real life applications. So that was all about the evolution part of the, evolutionary neural network, evolutionary fuzzy system and the modular neural network ensembles. Hybridization is even more vast. Hybridization is even more vast. The next thing that we would be carrying out, the next thing that we would be studying out is how do we combine, how do we hybridize the neural networks along with the fuzzy systems. And so how do we hybridize the neural network and the fuzzy systems, and then we would be studying in a bit of the adaptive neuro-fuzzy inference systems, which are completely fuzzy inference systems that use in a neural network architecture. So since they use a neural network architecture, I can use neural network training over it and evolve and get all the benefits of it. So that is what would be the agenda for the next of study, where we study in how to hybridize the neural network along with the fuzzy inference system.